So last lesson, we did finding the general solution for second order homogeneous differential equations. So this was the one where you write down the auxiliary equation, which will be a quadratic. You solve the quadratic, and then the number of roots that you get determines what form your general solution has. Okay, so remember there's three types. If you get two real distinct roots, it's a e to the power of one of your roots times x plus b e to the power of the other root times x. If you've got a repeated root, you get an ax plus b in the bracket and e to the power of that root times x. And if they're complex roots, you get e to the power of the real part times x. And then this a cos times the imaginary part plus b sine times the imaginary part. Okay, so the three forms that you need to know for homogeneous equations. Now, remember, homogeneous just means that it's equal to 0. Non-homogeneous is if it's not equal to 0, it's equal to a function of x instead. You still do the auxiliary equation method on the left-hand side of this. So you ignore the f of x bit to start off with, and you still do the auxiliary equation, getting the roots and so on. But what you also need to do is find what's called the particular integral of this equation, okay, which will depend on the form of your f of x on the right hand side. Okay, so there are some just to learn for this basically. This example one is kind of going to justify this a little bit. So here we've got a non-homogeneous second order differential equation. And notice the right hand side is 4 sine 2x. That's your f of x here. Okay. We've been asked to show that this equation here is a particular integral, a particular solution to this. Basically, we've been asked to show that if you substitute this in, it will satisfy this differential equation. Okay. So all I'm going to do is differentiate this twice and substitute it in. So why is that thing there? Differentiating this one. So differentiating sine goes to cos. I need to times by the 2, so it's minus 16 over 25 cos 2x. Cos differentiate the minus sine, so that will be plus 12 to 25 sine 2x. And if I differentiate this again, the differentiate cos goes to minus sine, so that's 32 over 25 sine 2x. Sine differentiates to cos, so plus 24 over 25 cos 2x. All I've done is differentiate that twice. And all I'm going to do now is take those derivatives and substitute them into the left-hand side of that differential equation and show that I get 4 sine 2x to show that this works. So d squared over dx squared I've got is 32 over 25 sine 2x plus 24 over 25 cos 2x. That's subbing into my d squared over dx squared. And I've got 3 times dy by dx, so that's minus 48 over 25 cos 2x. Plus 3 times that's 36 over 25 sine 2x. Could have chosen nicer numbers for me. And then I'm going to substitute the y equation in from this one, so times it by minus 4. So that will be plus 32 over 25 sine 2x. Plus 24 over 25 cos 2x. This is the left-hand side of this differential equation. You'll notice there's a bunch of coses and a bunch of sines, so we'll collect all of this up. The coses cancel out. I've got 24 plus 24 is 48, minus 48 over 25. They cancel. For the sines, I've got 32 plus 32, so 64 plus 36, that's 100 over 25. Which is 4 sine 2x. Which demonstrates that this equation for y is a particular solution to this, particular integral we call it. Okay. And I'll refer back to this in a bit for what this means. Now, this example 2 has just asked us to find a particular integral for this one. Okay. Now have a look at what we've just done. So what we've just done, the right-hand side was a function of x, it was a function of sine x. Our particular integral had sine 2x in it. It also had cos 2x in it because that cos 2x will differentiate to give you some sines. Okay. So if we're going to find a particular integral for this one, I'm going to guess what a particular integral will be. And I'm going to guess that it's going to be an e to the 7x, something times e to the 7x. Okay, because I know if I differentiate e to the 7x, I just get more e to the 7x. So I'm going to guess that my particular integral for this is a times e to the 7x. If I differentiate this, dy by dx is 7a e to the 7x. And if I differentiate it again, 49a e to the 7x. I can substitute these in now and work out what my a value is. D squared over dx squared is 49a e to the 7x. dy by dx is 7a e to 7x times up by minus 6, so minus 42a e to 7x. And I've got plus 9 times y, so 9a e to the 7x. So this is 49 minus 42, so 7 plus 9 gives me 16a e to the 7x. If I set this equal to the right-hand side, I can figure out what a is, because I've just got e to the 7x on both sides. Okay, so kind of cancel that off. Divide through by the 16 and get a is 1 over 8. This means that a particular integral for this is y equals 1 over 8 e to the 7x. Okay, and this is a solution. This works for me. Okay. This is basically what you have to do. Based on the right-hand side of your differential equation, you guess a particular integral for this. So if it's any type of trig, so if it's just sine or just cos or a mixture of sines and causes, you always guess that it's something sine plus something cos, like this one here. Okay, because of the fact that sine differentiates to cos and differentiates to sine, and when you substitute them, you'll get a mixture of those. When it's an e, you always guess that it's the same e times by a constant. So like we had e to the 7x there. So I guess that it's e to the 7x times something, and it works out. If you've just got a polynomial, so if you've got a quadratic or a linear one or something, you have to include all of the terms. So even if on the right-hand side you just had like just x squared, you'd still guess that your particular integral is something x squared plus something x plus something. Again, because those terms will differentiate to give extra ones. Okay. But here is a table. It's definitely worth learning these, because these are some common particular integrals that you're going to need. Yeah. There do exist other ones. Next lesson looks at trickier ones, but these are kind of the standard ones that it's worth learning. Okay. Yes,
So most of our last one,
yeah.
is there always going to be kx, not like kx and a different constant?
Yeah, they'll always be the same thing inside the trig. Yeah. So here are the steps for the full solution for a second order non-homogeneous differential equation. You first do what we did last lesson. So you do the auxiliary equation to find the general solution of the homogeneous part. This is what we call the complementary function. Don't ask me why it's called that, just is. You then do what we've just done and find a particular integral. And then the general solution for your whole differential equation is those two bits added together. And it's one of those things, don't think about it too hard, just learn that method and it gets you solutions. Okay. Let's have a look at this in practice. We're going to find the general solution to this one. The first thing to do is to find my complementary function, which I'm going to shorten to CF. To do that, that's looking at the left-hand side being equal to 0. So I get my auxiliary equation, got AE, I'm going to have lots of abbreviations here. And so my auxiliary equation, I've got lambda squared plus 6 lambda plus 9 equals 0. So that's the auxiliary equation for the left-hand side of this. You solve this on your calculator, this will have a repeated root at lambda equals -3. And so you would need to learn the forms that goes into. So this means that my complementary function is y equals e to the -3x and ax plus b. Usually it's a e to the one of your roots plus b to the other root, but that doesn't make sense here when it's repeated. So you have e to the -3x times ax plus b. Okay. That's your complementary function, just looking at the left-hand side, and then we're done with that. Now we're going to do the particular integral. Now the right-hand side is a linear function, so my particular integral is also going to be a linear function. So I'm going to put px plus q. And even if I just had 18x, I'd still need to include the plus q in there. I'm going to differentiate this twice. Give me p, and the second derivative just goes to 0. And then I'm going to substitute these in to work out values for p and q. So d squared by dx squared is 0, plus 6 times dy by dx, which is p, plus 9 times px plus q. So 9px plus 9q. And that's equal to your 18x plus 21. We can equate the coefficients here to work out p and q. So if I equate my x coefficients, I get 9p is equal to 18. So you get p equals 2. And if I equate my number terms, so I get 6p plus 9q equals 21. If p is 2, that's 12. And that gives you q. If p is 2, you get 12 plus 9q. Right, and 9q is really plus 21. Minus the 12 across and divide by 9 to get q. So our particular integral is y equals 2x. The general solution is you put these together. So you have y equals your complementary function, so e to the -3x, ax plus b, plus your particular integral. That's your overall general solution for this differential. Quite a few steps involved, but they're not too bad on their own, I don't think. It's just putting them on. And like I said, not thinking about it too much. Okay, so this one, start off with your complementary function. So do your auxiliary equation, which is lambda squared minus 4 lambda plus 3 equals 0. This will give you two solutions. You can solve it on your calculator, or you can factorize it. That's not right. -3 minus 1. I get two solutions, 3 and 1. This gives you that your complementary function has the form y equals a e to the 3x plus b e to the x. So it doesn't matter which one a and b is on. It can be either around. Your particular integral, then, you've got e to the -x on the right-hand side. So you're going to guess that this is, maybe I'll avoid using a just because I've already done it in. So p e to the -x, doesn't really matter. Differentiating gives you minus p e to the -x. Differentiating again takes you back to p e to the -x. Substitute these into your original equation, so you get p e to the minus x minus 4 times minus p, so it's plus 4p e to the minus x plus 3p e to the minus x plus 4e to the minus x. Obviously, all of your e to the minus x's cancel. You get 8p equals 40. So you get p equals 5. Your general solution at the end, then combine these together. So a e to the 3x plus b e to the x plus 5 e to the minus x is your general solution. Good luck. That one's involving trig. So do the same thing again. The complementary function I get by doing the auxiliary equation for the left-hand side. The lambda squared plus 6 lambda plus 25 equals 0. Right, to solve the we get complex roots for this one, so I get lambda equal to minus 3 plus or minus 5. Right. Remember, then your complementary function is y equals e to the minus 3x from your real part, and then a cos 4x from your imaginary part, plus b sine 4x. Okay, so that's the form you for complex roots your auxiliary equation. Then your particular integral. So you can choose y equals something. The right hand side is a function of sine 2x. So obviously you want sine 2x in here. But you don't just have sine 2x on its own. You also need to have cos in there as well. So I've got p sine 2x plus q cos 2x. You've got to remember to include both sine and cos. Let's differentiate this twice. 2p cos 2x minus 2q sine 2x, and we're going to differentiate this again. You get minus 4p sine 2x minus 4q cos 2x. Now that I've differentiated this twice, substitute it into your original differential equation. So, d squared over dx squared minus 4p sine 2x minus 4q cos 2x plus 6 dy by dx. So 6 times that is 12 cos 2x minus 12 q sine 2x. And then plus 25y plus 25 sine 2x plus 25 cos 2x, and that's equal to 195 sine 2x. And you've got to be really careful. It's really easy to make mistakes on this. I'm sorry for the mistake. So I'm hoping all of my causes cancel out, and they should do. I've missed. Sorry, they might not cancel out. They might just your values of p and q will cancel out. I've missed a q off that. That should be 25q cos 2x. Right, let's collect these up. My sine 2x, I've got minus 4p, minus 12q, 25p. And my cos 2x's, I've got minus 4q plus 12p plus 25q. And this is still equal to 195 sine 2x. We've got simultaneous equations for p and q here. So from my sine coefficient, that's 21p minus 12q equals 195. this one. From my cos coefficients, I've got 21q. I've got, let's try it again, 12p plus 21q equals 0. So solve these on your calculator. So I've got 21 minus 12, 195, 12, 21, 0. Gives me nice answers. So I get p equals 7. And q equals minus 2. Finally, write out your general solution for this equation. So I've got y equals e to the minus 3x, a cos 4x plus sine 4x from my complementary function, plus my particular integral, which is 7 sine 2x minus 4 cos 2x.